It's been quite a long time since I did my last video in the 65816 assembly tutorial series, and I still had a few topics I wanted to cover with that, so I wanted to continue today talking about interrupts. So the problem that I wanted to cover today with the sample program that we were working on, if you remember from the last video, animation in that is totally free running. That is that the speed of the spaceship as you're moving it around with the joystick, it's determined entirely by how fast the code is. So it'll move just as quickly as as that code runs. We'd like for the animation timing to be independent of how fast the code runs. Part of that is that we want it to be independent of the clock speed of the processor. And this was an old problem back in when you were programming the Apple II or the early PCs, when sometimes there'd be different clock speeds on different versions of the machines, and programs would run at different rates. Similarly with emulation, that's a problem now. So we want to avoid that. Also a problem is that the way that computer screens are displayed, how those images are displayed, you will sometimes get tearing of animated objects, as they're moving around the screen, if you're moving them while that section of the screen is being drawn. So we want to avoid that. That's the application for today in terms of the tutorial, and interrupts will help us with both of those problems. So the question is, to start with, what are interrupts? So on a real system, on an actual physical computer, from time to time, something that's outside the CPU will need to get the CPU's attention to request that some sort of process happens or something occurs. So some simple examples of that, let's say that the hard drive has some data ready to be read. It needs to send a signal to the CPU to say, hey, I've got the data, you can go ahead and copy it over. Similarly, you might have a timer on the computer that signals that either a certain time has been reached, or a certain amount of time has passed, or something along those lines. And that's what interrupts are for. It's a signal on the CPU that a device can trigger and say, hey, I need attention. And the way that the program or the operating system on the computer can deal with those interrupts is through a piece of software called an interrupt handler. They're kind of similar to subroutines, but they're coded a little bit differently because of how interrupts actually work. So the 65816, much like its predecessor, the 6502, has two interrupt lines. They're called NMI for non-maskable interrupt and IRQ for interrupt request. For either of them, if that line is pulled low, the CPU will see that interrupt has been requested and will stop processing whatever is currently running on the CPU and trigger the interrupt handler for that particular line to be started. Now, the interrupt request, IRQ, that is kind of the standard interrupt, and it's what's called a maskable interrupt. There is a bit in the processor status register that, when set, will prevent the CPU from processing any interrupt requests that it sees. If the bit is clear, then when the CPU sees a request on the interrupt on the IRQ line, it will go ahead and start processing that. NMI is a non-maskable interrupt, and as the name suggests, there's no interrupt bit that can prevent processing of NMI requests. NMIs are, generally speaking, for more critical events, things that really need to be processed in a timely manner. And we're not going to deal with NMI here, but it works in fundamentally the same way as IRQ. So what actually happens when an interrupt comes in? So the device will pull that IRQ line low, and the CPU will then check the I flag in the status register. If it's clear, it will go and push the program bank K, the program counter, and the status register to the stack. So those are storing the basic state of whatever program is currently running when that interrupt comes in. Next, it will set the I bit, and it will clear the D bit in the status register. So what that will do is it will mask any further IRQs, and it will also, if the processor happened to be in decimal mode, it will go back to binary mode for additions and subtractions. Then it will go up and look up the IRQ vector. So the IRQ vector is a pair of bytes, so 16-bit value, that is giving the address of the IRQ handler that should be executed. And so after it looks up the IRQ vector, the CPU will then transfer operation to that location in bank 0. Now, what I've described here is the behavior in the processor's native mode. I'm not really going to cover the emulated mode, but the emulation mode is a little bit different because 6586's got a bigger address space. Now, once that CPU has transferred execution to that address, the IRQ handler will then execute. And the IRQ handler's job is to determine what has caused the interrupt, because several different things can trigger an IRQ. And then it will go and do whatever processing is needed for that cause, and then it will return the state of execution back to the original program that was running and was interrupted. The way that it returns is through an RTI instruction. RTI is similar to RTL or RTS, except that it also deals with the processor status. So it will restore the processor status, the program counter, and the program bank register from the stack. So that will pull back that state that was saved when the interrupt came in, go back to the calling, to the program that was originally running. And I already mentioned that those vectors are 16 bits wide, and the handler code must be somewhere in bank 0. It doesn't really matter where it is in bank 0, but it must be there. Or at least the initial code for the handler needs to be there. You can have parts of the code being in other banks. You would just do in your handler a long jump or a long JS jump to subroutine to get there. Now, because IRQs are maskable, how do we mask or how do we enable and disable processing of IRQs? So that's with the I flag in the status register. And there are two instructions that we can use. There's SEI that sets the I flag and disables IRQ processing, so it masks the IRQ signal. And then there is CLI for clearing the I flag, and that re-enables interrupt processing. Generally speaking, the handler will almost never need to call these instructions. The reason for that is that the CPU itself will set the I bit when you go in to start running a handler. And the RTI instruction, when you're returning from the handler back to the main program, that will pull the status register back out of the stack that had been saved. And typically speaking, the I flag will be cleared there. So SEI and CLI are kind of implied usually by the operation of the CPU. Where you might use these instructions, however, is in the main program. If you've got some sort of critical operation happening that might take a couple of instructions, you would want to use SEI, and you need to prevent interrupts from happening there. SEI is what you'd use. You'd use SEI, do this critical behavior, and then do CLI to go back to processing interrupts. So it's typically called by the main program that's running. So some further details on how interrupts work. If an interrupt comes in while an instruction is being processed, which is honestly usually the case, the CPU will finish processing that instruction before checking for the interrupt and doing the interrupt processing. So it's really just between instructions that the interrupts are being examined and acted upon. The two exceptions to that are the MVN and MVP instructions. Because they're so long executing, the CPU will actually check in between each copy. So every byte that it copies as part of MVN or MVP, once it's copied that byte, it will then check for an interrupt before looping back and working on the next byte. And the CPU will save the status that was involved with MVN and MVP. And when you come back from the interrupt, that instruction, that MVN or MVP instruction, will carry on where it left off. So from the software's perspective, nothing happened. MVN and MVP have behaved as normally. but they were actually interrupted. In addition to the hardware interrupts that I've been talking about, there are actually some software interrupts on the 65816. One is the BRK, or break instruction. This was present on the 6502. And on the 6502 in an emulation mode, BRK actually is kind of like a software IRQ. It goes to the same vector. So the same vector handles both BRKs and IRQs. And on the 6502 in an emulation mode, there's an additional B bit in the status register that will be set if a BRK instruction had been triggered. And that's how your interrupt handler would tell if you had a break or IRQ. In 65816, in its native mode, again, which is what we're mainly been talking about, there are actually different vectors for break and for IRQ. So there's no B bit in the native mode. One other little weird detail with the break instruction, most assemblers will treat BRK as a single instruction that's basically implied addressing mode. There's no operand to it, so you just do BRK and that's it. The weird thing is that the CPU actually expects there to be a quote-unquote operand, a byte following BRK. So if the code that's handling the BRK interrupt returns, it will actually return to the second byte after the BRK opcode. So it will skip over a byte there. So typically, if you want to insert a BRK into your code and have some stuff come back, you would need to put some data byte after that. I often put a no-op after a BRK, or you can put BRK followed by a 0 or whatever. So it's kind of a weird little thing. I think it was intended to have an operand, and they never really did it, at least in the assemblers. Where BRK is often used is to go into the monitor. It's a break into the monitor. It can also be used by monitors or operating systems to insert breakpoints into the code, which is kind of where the name comes from. On the 65816, there's a second software interrupt after fashion. It's the COP instruction, COP. This does have an operand as well, and the assemblers actually include the operand this time. This goes to, again, a completely different vector for the interrupt. And what the COP instruction was originally for was for coprocessors. So if you had some sort of coprocessor hardware, like a math coprocessor or something, you could send it instructions using the COP instruction. But as with like a math coprocessor that might be optional, they put in a software interrupt so that if you try to do some sort of COP operation, like let's say you want to do a floating point multiplication or something, you'd issue the COP instruction to trigger that floating point multiply. If the coprocessor wasn't there to handle it, then the software interrupt could take over and get called by the COP instruction to handle it in software. So it's sort of a fallback. Again, we won't be using these today. I just mentioned them really in passing. All right, so some good handler practices. Because you are doing things kind of concurrently after fashion with the main program, it's really important to handle, kind of keep two things in mind with your interrupt handlers. One is to be careful to save the state of the main program that was running. So when the program is running, when your main program is running, it's using the accumulator X and Y and all these different registers and things. It's doing stuff in memory and everything else. So you want to be careful in your handler not to clobber those registers or to clobber that memory that your program might have been using, or to do so very carefully. And so one of the good practices is to always save your registers before you start working in your handler. So like the very first thing, save any registers that your handler might change. So, it's accumulator, that's X, that's Y, direct page register, the databank register. processor status and the data bank register, the program bank register have already been saved, so you don't need to worry about them. And then when you're about to return, just before you call your RTI, you want to pull those registers back. The other thing that's important is trying to keep the handler from taking too much time. You don't want to be doing a lot of extensive calculations or waiting or I/O that might take a lot of time. You don't want to be doing that in the handler. And the reason is twofold. One is that any time that your handler is taking up on the processor, that's time that's not being used by your main program. So that's preventing your main program from running and doing its job. The second reason is that if you've got interrupts that are periodic, and we'll be talking about one today, you only have so much time in which to do your work between those periodic interrupts. So you don't want to be taking so long in your interrupt handler that another interrupt comes in before you're done processing the first one. Then you're never going to finish. So yeah, you want to keep things pretty short in the handler itself. All right, so one little page here. I won't really talk about this in detail, but just wanted to mention where are the vectors for the different interrupt handlers. And I'm skipping a couple things like the reset vector and so on, but here are for NMI, IRQ, break, and cop, where are their vectors? Again, the vectors are 2 bytes each. The emulation vectors are where the 6502 vectors would have been, except for cop, that's not on the 6502. And these are the vectors that process those interrupts if you're in emulation mode. We will be working in native mode in this tutorial, and so on the right there, those are the native mode. Those are the native mode vectors over on the right. And one thing that you can see, if you look at the emulation vector for BRK, it's FFFE, and in IRQ, it's also FFFE. That's what I meant when I said that the two are using the same vector. Over on the native vector side, you see that there are actually 2 different ones, FFE6 and FFEE. Okay, so what's our example going to be today? We want to update the code for animating the spaceship so that, first of all, it animates smoothly, but also so that the animation is independent of the clock speed of the processor and the code, how fast the update code works. And there are a couple of different ways we could handle that, but one really convenient way is what's called the vertical blank or start of frame interrupt. So most graphics processing chips have got some way that they can trigger on every frame of the picture an interrupt. So the way an old CRT would have been drawn is that you have this electron beam that scans across from left to right and top to bottom over the actual screen. And when it gets to the bottom, it needs to go back up to the top. And that takes a certain amount of time. And so they turn off the beam and they send, they reset the voltages or the magnetic fields that are steering the beam. They reset that to go up to the top. And there's a certain amount of time that takes before they turn the beam back on again. And this is called the vertical blank period. And even an LCD monitor still understands that concept of a vertical blank and that vertical blank period where nothing is being drawn. And this is a convenient point for video display chips to trigger an interrupt and say, hey, right now, nothing is being drawn on the screen. We're in this vertical blank period. And Vicky on the Foenix machines has got the same concept. And this is handy in a couple of different ways. One is that it's kind of a regular quote-unquote clock for timing events to happen. Whatever your refresh rate is in that graphics mode, that's what that clock period is going to be on these vertical blanks. So for like 640 by 480, I believe Vicky uses a 60 hertz clock. So these vertical blanks will come in once every 1/60th of a second. So that's a really handy way of having kind of a regular pulse for controlling processing and doing different operations. The other thing is, because that's this vertical blank period where, quote unquote, the CRT beam, so to speak, has been turned off, where the screen's not being drawn, this marks a period where the screen's not being changed. And so if we need to make changes to the locations of sprites or change, what is being drawn on the screen, we can do so and not risk having that happen while a line is being refreshed on the screen and possibly having some sort of tearing artifact. So it's a way of getting somewhat smoother animation. So what we're going to do is we're going to update our code to use that to drive the updates to the sprites. So, to actually change the hardware register in Viki for where a sprite is located, we're going to do that actually in the interrupt handler for a vertical blank interrupt. And we can also use that to trigger the code to calculate our new positions. So the code loop that we had for checking the joystick, figuring out where the sprite should go, that will be triggered by the interrupt as well. We won't do it in the interrupt handler, but we'll have a way for the system to wait for that interrupt to come in. It will do its processing. It will update those sprite positions, and then when the interrupt comes in, the interrupt handler will look at the sprite positions and update the sprite. So that's what we're going to do. Let's get into that. All right, so here we have the code. It's going to be very similar to the code we did last time, but I've made a few modifications for the interrupts, and so that's what I'll focus on here. To start with, I have a different include file that I've added, interruptsdef.asm, and let me just take a quick look at that. Here we are. This is getting into the specifics of how the Foenix manages interrupts. So the 6502's got a single IRQ line, but there can be many devices inside the Foenix computer that can trigger interrupts, and can trigger interrupts in different ways. And we want to be able to process a particular one or something else, and we need to know which ones of these have actually sent the interrupt. As an example here, we have that starter frame or vertical blank interrupt that I had mentioned before. There's a startup line interrupt that comes from Viki. There are 3 different timers. There's a real-time clock. All these devices here, like the floppy drive, the mouse, they can all send interrupts. And these are codes. These are bits in a series of registers that are handled by the interrupt controller that's built into essentially the chipset on the Foenix. And there are basically 4 of these things. There's a pending register, a polarity register, the edge register, and a mask register. We don't care at the moment about polarity and edge. Pending indicates if a interrupt of a particular type is pending, awaiting processing, if it's been one of the things that's triggered the IRQ. And mask is just like the I bit in the status register that can mask IRQs. You can mask individual devices and prevent them from sending interrupts. And the way we talk in pending and mask registers about a particular interrupt is with one of these bits. And they are in groups. So 0 here, reg 0, is group 0, which is 8 different interrupts, or 8 different devices. And this first set of 8 here, those are block 0. That's that first group of interrupts. And that's where our starter frame interrupt is that we're going to be interested in. So that's bit 0. In register 0 is for that particular one. So this I pulled out of the kernel sources, but this information is published on the wiki for the Foenix machines, and I think it's documented fairly well. So that's what that is. I'm pulling those definitions for all those different bits and everything. I have added in a definition for IRQV. This is the address of the IRQ vector for native mode, and we're going to be setting that. Something I'm doing here, it's not strictly speaking necessary for this tutorial, but I'm putting it in because it can be a good practice to follow as well. I have set up a little variable location down here at 2000 of 2 bytes where I'm going to store the old value that was in IRQV. So before I set IRQV, I'm going to save it save the current value to this location. If this had been a real program that would then quit, you'd want to put that old IRQ vector back in, and so you need to save it somewhere, and that's what I got that for. This is all pretty much unchanged. And we can pretty much ignore this stuff here. This is all pretty much the same. But the first thing I'm going to, after I set up my direct page register and clear the screen, the next thing I'm going to do is I'm going to initialize that interrupt handler. And before I do that, I want to turn off interrupt processing because I don't want to have an interrupt come in when I'm in the middle of setting the IRQ vector. But then I also want to get everything kind of set up and ready to go, and then turn on the interrupts after that. So then I go into 16-bit mode. I pull out the value of the old address for the old interrupt vector, and I save that to old IRQ. So I've got that saved, and I could restore that later. And then I've got a section of code a little bit later on down called soft handle. So I pull the lower 16 bits of the address for soft handle into the accumulator, and I store that in IRQ vector. So that is me putting my own handler into the vector for the CPU. Next, I need to tell the interrupt controller in the Foenix chipset that I want to handle soft interrupts. And the way I do that is by working with the mask register. So the way the mask register works is that there's a bit for each device that it handles. If the bit is a 1, interrupts from that device will be ignored. So they won't actually trigger an IRQ. If it's a 0, then, like the I bit in the status register, if it's a 0, then an interrupt coming in from that device will actually result in an IRQ. So I want to drop or clear the bit for the soft interrupt. So I get the current value of the mask register, and I AND it with everything but the bit for the soft interrupt. So I'm basically going to turn that bit 0 into a 0, and then I store that back into the mask register. And I'm doing that with 8-bit accumulators because the interrupt controller for the Foenix, those registers are 8 bits. After that, my code initialization is pretty much the same, setting up the color lookup table, initializing the sprite bitmap, setting up the sprites, showing the sprites, setting the initial location of the sprite. That's all the same. But notice, if you've recently seen the other video, you might remember that I had a JSR here to go and actually change the hardware registers in Wiki for that location. And I'm not doing that here because I have moved all of that into my interrupt handler. So let me go down to the interrupt handler and show you what that looks like. So that is down here at the bottom. You'll notice that I've changed my origin to a little bit after those variables that I'm storing, and in bank 0. So that's, again, important. The interrupt handler has to be in bank 0, or at least has to start there. And here's my interrupt handler. So I'm not really doing anything terribly exciting here. I set 16-bit accumulator, and I push whatever is in the accumulator to the stack. The reason I'm doing that is that the accumulator X and Y, those registers are not saved by the CPU automatically when interrupt gets processed. So our interrupt handler, if it's going to use the accumulator, which we do, then you really need to save that before you start doing stuff. And I'm going to save that in 16-bit mode just in case whatever was running and interrupted happened to be in a 16-bit accumulator. I need to make sure I save that upper 8 bits. So after I've done that, I go back to 8-bit mode, and now I want to look at the pending register, and I want to see, is bit 0 set on that pending register? So the pending register is doing double duty. When you read from it, a 1 in a bit indicates that the corresponding device has requested an interrupt. So I take that pending register and I AND it with the bit for soft, and I check to see, is that bit set? And if so, I'm going to go ahead and process that interrupt. If not, I need to skip processing it, and I'll get into what we do in a second there. So let's say that the interrupt did come in from SOF. So what we want to do is we want to update our sprite position. So we want to take this opportunity when the screen is being refreshed to go and change the hardware registers. And so I grab the X coordinate and I save that to Vicky. I grab the Y coordinate and I save that to Vicky. And now I've basically done my interrupt handling for our spaceship. And so now what I need to do is I need to go back to the interrupt controller on the Foenix, and I need to acknowledge that the interrupt has been processed. Now, multiple interrupts can come in at more or less the same time. Other things can be happening. And generally speaking, we want to clear all of that. We don't want to clear that if we are going to process that later. But in this particular case, we're only handling soft interrupts. We don't really care about the other ones. So what I do here is I go back to 8-bit mode, I grab the pending register, so I see all of the pending interrupts, and that includes the soft interrupt that we've just handled. And I need to acknowledge it and clear that pending register. And the way you do that, this is a little curious the way this happens. When you write to the pending register, if you write a 1 to a bit, that will indicate that you have handled that particular interrupt, that particular device. And so that will clear the pending bit. So basically what we're doing here is we're taking the pending register for group 0, and we're basically writing it back to itself, and that will clear all of the pending registers, all of the pending interrupt bits, including the soft that we have actually processed. Now again, this is not generally speaking what you would do on the Foenix, and this really isn't a 65-bit16 thing. This is all about that interrupt controller that the Foenix has. A more targeted way of doing it would be just to write the bit for SOF, just writing that bit back to the pending register and saying, hey, we have handled this, clear that bit out. Once that's done, we need to return. So we're going to go and pull the accumulator back that we saved. We saved it up here. So now we're going to restore it, and we do RTI. So RTI, again, it works like RTS or RTL, but this is a return from interrupt. So it also pulls back and restores the status register. So you notice I've changed the status register quite a bit here, changing the sizes of the accumulator that we've been handling. I haven't been worried about saving the processor status because that was already done by the CPU early on. All right, so then we go back up to our code, our main code. So again, we go and we store in our variables the location of the sprite, but we don't update the registers just then. And instead what we do is we're going to go now and enter into our loop. And what we want to do in our input loop is, first of all, we want to re-enable the interrupts. And then we're going to wait. So this is an instruction. I haven't really talked about this yet. There's an additional instruction on the 65-bit16 called WAI for wait. This actually puts the processor into kind of a sleeping mode. It won't execute anything until an interrupt comes in, either an IRQ or an NMI. And so we'll now sit here and we'll wait until the next vertical blank period comes in on the screen. That will trigger an interrupt, and two things will happen. Because I re-enabled the IRQs here, that interrupt will trigger our interrupt handler. So we'll pop down here to soft handle, we'll run through all of this, and then here's where we take that 100-100 that we had set in the setup code, and we stick that in the hardware registers on the Vicky, and that's when that sprite gets put into position. You could think about it sort of simultaneously. This wait instruction will complete, and we'll start executing the code here. And this is, again, the same code we had before, where we look at the joystick and we check to see are we moving up or down or left or right or whatever. And here's our kind of our loop where we're waiting for user input. It doesn't really matter that we're clearing the interrupt each time, but we will wait for an interrupt, check the joysticks, go back, stop and wait for an interrupt, check the joysticks, and so on and so on. So every 60 times a second, we'll go through this loop here. Now, if we've gotten input, let's say we're going down. Now we go and do the down section. And here I'm doing something I am calling SEI again. The reason for this is that we're going to be changing, potentially, or at least looking at, a variable that is also being looked at by the interrupt handler. Conceivably, the interrupt could come in here. Now, it's not really going to happen in this particular code, but again, good practice. This is a point where an interrupt could come in here after we've read SP0Y and are changing it, and before we set SP0Y. And so a change, if an interrupt comes in here that then changes SP0Y midstream, that can cause a problem here. It's called a race condition, where you are looking at a value and you're assuming it's not going to change before you do something, but an interrupt might come in during that time that could change that value. We want to prevent that, so we set the interrupt here before we start working with that value. So we set the interrupt, we look at SPY, we go and we calculate, we're going down, so we add the velocity on to the value, we do all of our little checks and everything else. And when everything is fine, then we set the new Y value here in our variable, and we continue with the other checks. But let's assume for the moment that no other input is required. So we will then come up to get input again, where we again re-enable interrupts and we wait for an interrupt. And so when the interrupt comes in, we're now going to take that new Y value that we had set in the variable and we stick that in the hardware registers in Vicky, and the sprite will have moved. So that's how that's working. We can look at this as this get input loop here is kind of happening in our main program, and periodically something comes in, interrupts it, and updates the registers there. But this loop is also waiting for that interrupt, and so its calculations are synced up to the interrupt. We didn't actually need to do that particularly, but it could be a good way of handling, kind of doing timed events in your code and doing calculations based on time. So anyway, let's pause for a moment. Let me switch screens so that you can see how this code looks actually running. All right, so now I will send the code over. And there's our sprite, and we're already getting interrupts. So I can now, use the joystick and move it around. I don't know if this will come across with the screen capture, but to my eye, the sprite is moving a little bit more smoothly than it did before, because it doesn't ever update the sprite's position while that section of the screen is being drawn by the LCD screen. So to my eye, it's a little smoother, but with image capture and YouTube going in there and doing its algorithm stuff, you might not see that in quite the same way that I do. But anyway, so not a very exciting demo. It looks pretty much the same as it did before, maybe a little bit smoother, but it does show how interrupts work, and we can then start doing some stuff differently in the next video. Part of the reason why I wanted to do the interrupts here is that we're going to actually add some more animation stuff in here into the tutorial with the next set of topics. I'm going to start adding in things like another spaceship, or player missile, like a little missile graphic or something like that, and having interrupts in there doing the animation. We'll expand how the interrupt handler works so that it can actually process multiple moving objects that are moving in different directions, and have that handled in a very clean manner. So I hope you found this interesting. I hope it was useful to you, and thank you very much for watching.